The potential on the surface of a spherical shape, I'm assuming, sphere radius r, is given by v equal v0 cosine 2 theta. This is a boundary condition. Assume as r goes to infinity, the potential is 0. Also assume there's no charge in or outside, so all charge is on the shell surface. Oh, okay, so this is a spherical shell. And we need to find the potential everywhere inside and outside the sphere. Okay, so I did record another video how to solve. So basically what we need to do here is solve Laplace's equation. I've done it in separate recordings in rectangular coordinates, 2D, 3D, and in spherical coordinates. If you're interested how to derive the formula for the potential in spherical coordinates by solving Laplace's equation in spherical coordinates, here we're just gonna go to the result and use the result as is. This is the result. It's basically a summation of Legendre polynomials of various terms that will give us the potential. So I'm gonna go ahead and use the result. If you're interested on how we got here, how we got to this is the solution of Laplace's equation in spherical coordinates. You can check this out on one of my videos where I've actually went and derived this. Okay, we will start inside the shell and we'll work our way out to find the potential. So inside, i.e. that's where r is less than or equal to capital R. Okay, we know for this case at the center where r equals 0, this term here becomes 0. So if this term becomes 0, we get BL over 0, which is infinity. So this term would blow up. For that not to happen, we do have to set, in this case, BL equals 0. Okay, so that prevents the second term in the summation from blowing up at the center. So my V there would become AL R to the L. Okay. Now let me use the boundary condition, the fact that at the surface, right, my potential is V0 cosine 2 theta. So that means VR theta, so I would replace small r with capital R, from L equals 0 to infinity. So the objective here is to find the coefficients AL, okay? AL, RL, okay? And this has to equal apologies, I forgot the PL cosine theta, the Legendre polynomials. So let me stick that here. Okay, and this has to equal V0 cosine 2 theta at the surface. V0 cosine 2 theta. Okay, now so now the question is, can I satisfy this equation if I were to choose the appropriate ALs? And the answer is yes. The reason is because the Legendre polynomials make up a complete set of functions. i.e. on the interval where x is between -1 and 1, or where theta is between 0 and pi, right? They are a complete set of functions. So and the way to find those constants is we use a trick often referred to as the Fourier trick. Okay, and the reason that this Fourier trick works is because the Legendre polynomials are orthogonal functions, i.e. if I were to integrate, so I'll get back to this equation here, let's call it equation 1, I'll come back to it, but on the side note, since the Legendre polynomials are orthogonal functions, if I were to integrate the Legendre polynomials from -1 to 1 on the interval -1 to 1, PLX PL prime x dx, it's the same thing as doing if x happens to be an angle, right, where x is cosine theta, so this would be so I would replace x with cosine theta, and then I would be integrating from 0 to pi, right, and then this is PL prime cosine theta, except now because x is cosine, the derivative would be sine theta d theta, so dx turns to sine theta d theta, and if I were to integrate these two, the answer would be well, if L prime does not equal to L, i.e. if they're different, the answer is 0 anytime they're different, and if they're the same, the answer would be 2 over 2L plus 1. Okay, so I'm going to exploit this relationship of orthogonality of the Legendre polynomials in equation 1 in order to find the coefficients A of L. So what I would do is I would multiply equation 1 on both sides. So equation 1, so back to equation 1, okay, equation 1 is this green equation here. I'll rewrite it here to show you how I'm going to do this. Remember, we're on the surface now. And this is, okay, let me leave some space, okay, and V0, okay, so what I'm gonna do is I will multiply here by PL prime cosine theta on the left, okay, and I will do the same exact thing on the right. Okay, and I will integrate. So technically this here would be a summation on L prime, okay, and I will integrate this. These are constants, so they can come out. D theta or sine theta d theta. So I should have added here sine theta d theta, and here sine theta. Let me okay, and I will integrate, oops, sorry, the integral, this guy depends on theta, so 0 to pi, 0 to pi. Okay, fair enough. And we said that if L does not equal L prime, this whole thing will be 0. So the only place it will work is if L equals L prime. And if L equals L prime, the answer to this will become AL RL, and this guy here became 2 over 2L plus 1, or L prime, whatever you want to use. Okay, and here we do have to integrate, so I do have to integrate this side. So remember, L equals L prime, and I will have cosine 2 theta PL cosine theta sine theta d theta from 0 to pi. Okay, and so now I could find what AL is. Right? So my AL will be V0 over 2 RL, and we have here a 2L plus 1, and we have here 0 to pi cosine 2 theta d theta. We just don't know what L is, but I will come back to that. Okay, so L is an unknown at this point. Okay, now this is one equation. Now going back to boundary conditions, the other thing, so now I'm gonna go outside the sphere, right? I'm gonna go outside now, and that's where r is greater than the radius. Now right off the bat, if you look back at the question, it said as r goes to infinity, v goes to 0. Now if r goes to infinity, the first term in the summation would go to infinity. If L is, because L is positive, it goes from 0 to infinity, correct? So so that means for this not to happen, because I need this to go to 0, then AL has to be 0 in this case. Okay, so here AL has to go to 0. AL has to equal 0. Okay, so then my V r theta becomes the second part of the equation, just BL over RL plus 1 PL cosine theta. Now continuity at the surface demands that the two potentials would be the same, right? So continuity of V at the surface. So BL over R L plus 1 has to equal V0 cosine 2 theta. Okay, I can do even better just to make the algebra a little bit more straightforward. What I could do is, rather than setting it equal to V0 cosine 2 theta, I know that it's got to be the same as the V from the inside, which is the blue expression here, ALRLPL cosine theta. That's just faster to solve it. So this would be AL, right? RL, sorry, AL, RL, by the way, this here is, how did I get L in the power? That's not correct. This is, I didn't mean for this to happen, but this here is down here, down here, okay, down here, down here, down here, okay. It's a it's not a power, it's an index. Okay, it's AL. Okay, so back to here. So this is ALRL PL cosine theta. Okay, well, if these two were to be equal, therefore the coefficients have to be the same, right? So in other words, this has to equal this. Has to. Okay, so that means BL over R L plus 1 has to equal, oh, this is happening at the surface, by the way, so I need capital R here. So this is equal AL RL, cross multiply, and you get BL equal AL R to the 2L plus 1. So this is a relationship between AL and BL, meaning if I can find out what AL is, I could find BL right away. Okay, so now that I have them related, let me go back to this gold equation here, and let me call this equation 2, and let me work on the equation 2 because I'm gonna get AL out of equation 2. Okay, so notice this cosine 2 theta here. Okay, so this is gonna be, so equation 2 becomes AL is equal to V0 over 2RL times 2L plus 1. Okay, now notice this cosine 2 theta is the same thing as 2 cosine squared theta minus 1. Okay, so this is a trig identity. I replaced cosine 2 theta with 2 cosine squared theta minus 1. Okay, and then I have PL cosine theta sine theta d theta. Okay, so I'm gonna FOIL this integral. Okay, let me actually do it on the side. I'm gonna take this piece here and work with it on the side. Okay, so let me work with this here to show you what this is. So if I split this up, this is 0 to pi 2 cosine squared theta PL cosine theta actually one moment, let me do something better than this, probably shorter. I'm gonna turn this cosine squared into a Legendre polynomial. Okay, I know that my second Legendre polynomial P2 of cosine theta is equal to 3x squared, so this would be 3 cosine squared theta minus 1 over 2. So if I turn this around and solve for cosine squared theta, I get cosine squared theta equals 2p2 plus 1 over 3. And so now I will replace this cosine squared here with this, okay, because that will enable me to integrate PL of cosine, which will tell me what L is. Okay, so my integral becomes, so now 0 to pi, so now instead of cosine squared I will put down multiplying by 2, so this becomes 4p2 of cosine theta plus 2 over 3, and then I have minus 1, okay, and this is PL cosine theta sine theta d theta. Okay, and now I will split up the integral. So first let's just do a common denominator here. This becomes wait, is this minus or plus 2 cosine squared? Yeah, I think it's minus, but I just want to check because everything is riding on the truthfulness of this trig identity. Yes, it's correct. So this becomes so minus 3, so this becomes 4 p2 cosine theta. So plus 2 minus 3 becomes minus 1 times 1/3. Okay. PL okay, and now I'm gonna split it, so this becomes 1/3, and then I have 4 p2 cosine theta PL cosine theta sine theta d theta, so that's one integral from 0 to pi minus, right? Now notice 1 is the same exact thing as P0, right? Which would be P0 of cosine theta is 1 times PL okay, good, we're close. Now remember, back to the orthogonality conditions. This integral vanishes except when L prime and L are the same. Okay, so in other words, this here will be I should have put a summation here, by the way, right? Because this is, let me see here what happened. Yeah, I just forgot a summation here, so this is gonna be, because I'm summing up overall L, so there's supposed to be a summation here. Not that it's gonna matter in the answer, but let's just be accurate here. Okay, so back down here, So there was a summation here. Okay, so now that means when I integrate this, I don't care what all the other L's are. If this guy L does not equal to 2, which is our L prime, all the other terms will be 0, and the only term that will survive is here, is when L equal 2, right? And the rest will be zeros. And the same exact thing can be said here. All the terms will be 0 except when L equals 0 here, because our L prime is 0. So here L equals 0. Going back to equation 2, remember AL is, we have a summation here, and only 2 terms in the summation survived. So if L is 0, I will get, so this is V0 to L plus 1 V0 V0 over now keep in mind here, when L is 2 on the first, the second term goes away because L is 0 there, it does not equal 2, and vice versa. And when the second term survives, i.e. when L is 0, the first term goes away because L there is 2. Okay, so I'm going to go back to equation 2, and I'm going to rewrite this as V0 over 2R to the L, okay, 2L plus 1, okay, times 1/3, okay, and now I'm going to open bracket, and this is going to be 4. Now when L equal 2 and the rest are 0, I could represent this as L2. This is the delta function. That's saying it's 0 everywhere except when L equals 2. I have a term, okay, minus the second term. This would be delta L0. Okay, delta L0. Okay, fair enough. So now let's see. So this is AL. Okay, so A will equal to, now if L is 2, right, I'm gonna get let's see here. So the answer to this was 4 times 2/5, right? So we get V0. So now L equal 2 here, okay, on the first one. So the second one will go away. And if L is 2, let's do the 0 first, probably be easier, yeah. If L is 0, then this becomes V0 over 2, and then I get 1/3, and then the first term will be 0, and the second term will be 1 multiplied by -2, because that is 2 over 2L plus 1. So 1/3 times -2, so this would cancel, and we would get minus V0 over 3. That's if L is 2. Okay, so this would be and then if L is 2, then the second term would go away, and then I would get V0. So this is, here is my answer to this. So this would be V0 over 2R squared, and then this is a 5, and then I have a 1/3, and I have a 4, right? Wait 1 second, where's the 4? Where did this 4 come from? Yeah, and I have 2/5, 4 and 2/5, 4 and 2/5. Okay, so this goes away, and I will get 4 v0 over 3r squared. So these are my two answers for my AL. Okay. Okay, so that means now that I found my AL, I could figure out what my V is on the inside, right? Because that was for the inside. So that means V. Actually, let's find BL and then we can just write them together. So now BL that I found AL is they're related. So it's just that times R to the 2L plus 1. AL R to the 2L plus 1. So now again, there's going to be two answers. If L is 0, then this is just going to be minus V0R over 3, and if L is 2, this is gonna be 4v0 over 3. Now r squared, and I'm gonna multiply this by 2, 4, 5, r to the 5th. So this is gonna be r cubed. Okay, because this is 5 to 4, 5, and r squared, yeah, r cubed. Okay, fair enough. So now I just plug those into the equations inside and outside, right? So inside, so therefore VR theta will equal this is gonna be AL R to the L, so AL, so let's say if L is 0, this is gonna be minus V0 over 3, okay, times RL, which would be R to the 0, which is 1, and P0 of cosine theta, that is just 1, right? P0 of cosine, yeah, that's just 1. Okay, plus, now if L is 2, this is gonna be 4v0 over 3r squared multiplied by r to the L, so this is r squared, and this is gonna be P2 cosine theta, and we know exactly what this is from the table. This is just 3 cosine squared theta minus 1 over 2, right? So let me actually write it as such. So this is gonna be 3, so this second term here is multiplied by 3 cosine squared theta minus 1 over 2. Okay, so this is the potential inside for R less than or equal to R, and now for R greater than R, let's do this in blue. So so this is going to be BL, so BL, if L is 0, this is going to be minus V0 R over 3, right? And this is divided by RL plus 1, so that's just R if L is 0, and this is going to be P0 cosine theta, which is 1, plus, now if L is 2, this is going to be 4v0 r cubed over 3, and this is divided by r to the L plus 1, so this would be r cubed Okay, and this is again p, this is the same thing, 3 cosine squared theta, second legendary polynomial, over 2, and this is for r greater than or equal to r. So this does it for solving for the potential inside and outside.